Recording in progress.
So we have 13 people. Looks like several more people are coming to the webinar. So we can wait for another minute. Yeah.
Good morning, Angela.
Yeah, Federico. Yes, you can.
Hi, good morning.
So Federico introduced your group, Denmark, together with you. How he
Yes.
engaged with you?
So it's all thanks to Klaus.
I see.
Yes. Klaus is our department head. And Federico, you were his students in the past, is it?
That's correct. Yeah.
Yeah, Klaus said that you are one of the best students he ever had.
He's very kind. But yeah, I did one work with Klaus as well. We did some collaboration as well here. We had Victoria, who came to UTS for an exchange. So anyway, it's good to get people all together.
Yeah, right. Still, yeah, we are collaborating together. Yeah.
Yeah.
So we are not so far away at all.
So can I start? If Angela agree? All right. Hello, everybody. This is my great pleasure to moderate this scientific and industry webinar series. So today we have a speaker from Denmark, the Associate Professor Wenjin Zhang. So she will talk about functional material and membrane design for water technology. So let me briefly explain for her bio. So Dr. Wenjin Zhang is an associate professor in the Department of Environmental Engineering at the Technology University of Denmark, so where she is leading a research group and a laboratory focusing on advanced materials and membrane design for water and energy technologies. Dr. Zhang received her MSc in physics in 2005 and then PhD in chemical engineering in 2009 at Hong Kong University of Science and Technology. Before joining the DTU, she was a research associate at Vanderbilt University in the United States, where she combined the functional nanomaterials synthesis, electron spinning, and electrochemistry to design the world's first ever fuel cell nanofiber electrodes. To acknowledge her contribution to the fuel cell industry, the Electrochemical Society (ECS) awarded her the prestigious ECS Denora Industrial Electrochemical Award 2011. In 2013, Dr. Zhang won the funding from Hans Christian Ørsted Fellowship to lead the electrospinning technology at DTU and design high-performance ceramic membrane and catalyst for energy technologies. In 2019, Dr. Zhang embraced the new opportunities and joined the DTU environment as an associate professor, focusing her research on Advanced Material and Membrane Design for Water Technologies. In 2020, Dr. Zhang received her award from DTU Executive Board to start executive MBA education in Management of Technology at DTU. So she will talk about her expertise for today. Also, this webinar series is co-organized by AIC Research Hub, the Energy Efficient Separation, Monash Membrane Innovation Center, Membrane Society of Australasia. So just announcement for this webinar. So make sure you are keeping your microphone on mute. And if you have any questions, so please utilize your chat box. And then after her presentation, so we can go for the Q&A session. Angela, now the floor is yours. Please join me welcoming her presentation.
Thank you very much, Professor Zhang. Thank you, everyone, for joining this webinar. Please let me to share my screen first. Now, so as Professor Zhang just introduced, I'm Zhang Wenjin. You can also call me Angela. And today, I would like to take you to the platform we established at DTU, where we use advanced materials and membrane for water technology. So first, a little bit about me on the side of the materials. So I was born in the northern part of China, and at the age of 18, I went to the south part of China, the South China University of Technology. So originally I was trained as a polymer scientist. And then there I learned the polymer chemistry and physics, and also with some processing technologies. I was lucky enough to receive the fellowship from Hong Kong government and join Hong Kong University of Science and Technology. For my master, I studied the composites, where combine the ceramic nanofillers and put it into polymer to reinforce the polymer materials. For my PhD, I get access to the functionalities of polymers, use ion exchange membrane to conduct the protons in the fuel cells. So I was fascinated by the interplay of the functionalities and the structures of the polymers. So right after my PhD, then I moved to the United States and joined Vanderbilt University. There, I studied metal as a catalyst with carbon support. And I use electron spinning as a shaping technology to invent the world's first nanofiber electrode for fuel cells. So at that time, I was thinking there is still one more materials I haven't studied yet. That's why after the postdoc at Vanderbilt University, I moved to Denmark and joined the Department of Energy. There, for 6 years, I work on the ceramics. So I combined the sol-gel chemistry with shaping technology like electron spinning to make the ceramic nanofiber membrane for solid oxide fuel cells, electrolysis, and also flue gas purification. So over the years, I also had the opportunity to collaborate with scientists and entrepreneurs in Denmark for water technology. I discovered there is tremendous opportunity for advanced materials and membrane structures to address challenge for water. That's why 2 years ago, I joined DTU Department of Environmental Engineering. There, I become associate professor and also group leader. So for us, we want to establish the platform for the material design. And I think there are 4 pillars: synthesis, structuring, functionality, and process. And we combine these four pillars to design materials for a specific application, like water purification, wastewater treatment. Like in the gas phase, it can be the filters as well, and for sensors and for energy, such as fuel cells and batteries. I'm quite lucky to have very competent group. In that group, I have one leg on the clean energy, mainly because of my history in the DTU energy. I still have several PhD students working on fuel cells, battery, and also the gas separation and fuel storage. And over the past 2 years, I got actually quite a nice group for the clean water as well. For instance, I have Yibo Dou, who is a scientist in my group and working on piezo and photocatalysts. And Dan is a PhD student working on enzymatic membrane reactor for water treatment. And also 3 PhD students working on the photocatalyst for the micropollutants and the microplastic degradation in water. And Jianwen is working on the electrochemical way to treat wastewater. And Xinchen and Xihui Hu, they are the students especially tackle the polymer physics, try to reinforce the polymer nanofiber membrane for the filtration in water. I also have a close collaboration with Klaus group and the 2 postdocs, Karina working on the process and Sigurd working on the molecular dynamic simulation. So here is a list of selected papers over the 2 years. And you can see some keywords here like contaminant removal in water. This is fuel cells, nanofiber electrode, biogas upgrading, storage, solar acid fuel cells, and also the forward osmosis. They are very much different, but they are also quite similar in the morphology. It's kind of 1D nanofiber. That's why I want to also mention or highlight one of the shaping technology we use in our lab, that is electron spinning. Electron spinning is very efficient technology to make the nanofiber materials. And what you do is you often start with one of the polymer solution, about 5 or to 15 weight%, and then you push it through metal needles. And this needle will form the droplets at the end. If you apply the voltage, and they will generate electrostatic force and elongate these droplets of polymer solution into a nanofiber. So one see it is quite slow, but if we put it in motion, you can see it's very efficient. With a constant supply of polymer solution, once you apply the voltage, you will have a generation of nanofiber waterfalls. If you put substrate on the other side and ground it, all your nanofibers will aim at this substrates and form the nanofiber. For instance, you play with your substrate, you can have 3-dimensional nanofiber membranes, or you can have super aligned, where you can introduce a preferential orientation of the functionality, like proton conductance or the thermal conductivities. You can also create a cold shell structure where you can actually enhance the surface area, or you can encapsulate the active chemicals inside of a nanosphere. This is more on the microscopic scale to design the structures. In our lab, we also look into another scale to shape these structures. So when we do electron spinning, and actually what is happening is that there is a continuous stretching of this polymer solution. So this is, for instance, from the very beginning, the polymer chains are more randomly oriented. But during the flight between the needles and your collectors, you will see the polymer chains intend to be elongated and stretch and form a certain orientation. And this process is very strongly related to the air surrounding or inside or that is contain your electron spinning process, and temperature and relative humidity, because that will determine the evaporation of the solvent and also how much you can stretch and orientate your polymer chains. So to do that, we have the facilities in our lab. First, we have 2 electron spinning equipment. On the left, you will see the black ones is needle-based electron spinning. There we can do, for instance, 3-dimensional or super-aligned nanofibers, coaxial structures, or co-electron spinning with different polymers. This is more for the student to try their crazy ideas and have the smaller scale. On the right-hand side, this is a Marco, and that is commercial equipment for needle-laser-based electron spinning. So the idea is that if student can design a solution or the process, they can do the upscaling in this equipment as well. Can do the row-to-row productions. We can also show the investors or industrial collaborator, they can always move to the next scale, the industrial scale electron spinning process as well. But to precisely control the molecular orientation of each nanofiber, what we can do in a lab is to couple this electron spinning equipment with air conditioning unit, also from Marco. Here we synthesize our own air with controlled temperature and relative humidity. So in that case, we supply the air into these chambers, and we can control the evaporation and elongation process during the electron spinning to improve the orientation of a polymer chain. And the outcome would be super high mechanical properties, thermal conductivity, and for some functional polymers, you can also enhance the ion conduction paths. So those are the from structure point of view, and also we have different materials to play with. For instance, here is pure polymer. It's a polyphenol sulfone nanofiber membrane. With post-treatment technologies, we can create this interconnected 3-dimensional nanoporous membranes, and they're very strong, so it's super good for the support from forward osmosis membranes. And the second one I want to show you is quite interesting. The core of the fiber is still polymer, so overall it's very flexible. And what we can do is to use in situ growth to grow the nanoparticles on the surface of nanofiber. Here is a metal organic framework for the absorption of the contaminants or for the gas storage. And the idea is that by putting those functional particles right on the surface of nanofiber, we will be able to facilitate the mass transport and get direct in contact between the particles or catalyst with the gas or liquids we want to have a reaction with. If you take those kind of materials and carbonize it, and what you get is a kind of carbon nanofiber. And with metal organic framework, you can also produce nano-sized metal catalyst that decorate on the surface of carbon nanofiber with tremendous amount of surface area. Instead of carbonization, if you combine sodium chemistry with the calcination and sintering process, what you get is a ceramic nanofiber membranes. For instance, titanium dioxide or some of the LSC, the peroxide ceramic as well, to introduce the ion conduction functionalities. So now I have introduced you the shaping technology, electron spinning with the structuring and also materials we can play with. And now I want to introduce water into our work. I checked the registration list. Then I understand the audience has quite a broad background. So I select these two projects and also try to stay at a conceptual level. But if you have more specific questions in some of the characterization or specifications, you're more than welcome to ask or contact me later on, and we can dive into the details. So the two projects, first one is to combine the absorption and the photocatalysis to treat the wastewater from pharmaceutical industry. So micropollutants has become quite a severe problem in our environmental engineering, especially for the pharmaceuticals of emerging concern in aquatic system. And the source can be the agriculture's or industrial influence or hospital influence. For instance, in this review articles, and you can see that in the countries, here the color indicates the number of pharmaceuticals detected in the surface water, groundwater, tap water, or even drinking waters. So especially for some developed countries like Europe, North America, Australia also, and Asia. So how those pharmaceuticals often they have quite a small molecular size and low concentration. And for the wastewater or conventional wastewater treatment plants, the removal efficiency sometimes below 50%. That's why they can penetrate our conventional water treatment technology. And there is a call for the innovation to try to tackle this challenge. And one of the research direction is on the absorption. So instead of using very dense film to filter out these small molecules at very low concentration, how about we use absorbents and actively take those molecules out of the water? For instance, one of the most studied 2D material, LDH, they can be utilized as absorbents. They're very low cost, has high surface area, and also non-toxic. But a challenge is that the absorption activity is still low. And often when people do experiment, they use as a powder. So it's a mix of the powder with wastewater and try to have the absorption. And afterwards, still there is additional step, separation. Try to remove those powder from treated water as well. So there is always a concern if there are any leaching of this such a powder into the water. And another challenge is that the saturation. So once it's absorbed enough pollutants, and what do? Is that we need additional chemicals to regenerate, and that raises concerns for the harsh chemicals in the environment as well. Or some people just try to dump it into the landfill, then the additional pollution might happen as well. So our concept here is that first, can we make it better? So by some doping of the LDH, we want to enhance the absorption capacity of this 2D LDH. And second, we want to immobilize it. We want to put this LDH immobilize onto a nanofiber membranes. And in that case, when the water flows through, we break them down into micro-sized water ponds, and they have the direct in contact with LDH absorbents. And the third is that, how about regeneration? If our LDH has photocatalytic properties, then once it's saturated with micropollutants, we just need to introduce the light and induce the in situ degradation of micropollutants, so we can regenerate our absorbent in that way. But those are the concepts, and we start with synthesis and structuring. So what we have is, as a beginning is polymer nanofibers, is PNA nanofiber in this case. And then we deep coat with aluminum hydroxide. Afterwards, it will have the in situ growth of a ZFL on top. It's kind of leaf structures. And then we do the ion exchange to make cobalt, nickel, copper, LDH nanofibers. So at the end, you can see this photos here. We get like algae green nanofiber membranes. It's still very flexible because at the core of each nanofiber is a PNN, a polymer. And if you zoom in, and you can see for each nanofiber, they are roughened by those LDH structures at a very large surface area. So here, I won't go too much in details, but just to show that we have XRD and the TM to show the crystalline structures of this 2D LDH. We can also see the homogeneous distribution of cobalt, nickel, and the copper throughout the surface of nanofibers by XPS, and we can see the influence of the copper that modify the electronic microenvironment of LDH to introduce the oxygen vacancy. And then we put it into work. On the left-hand side, you can see this is 4 different kind of nanofiber membranes we put into the solution with HCTZ. This is one of the pharmaceuticals used for the blood pressure regulator. And they are found in many places, for instance, in Portugal, in Sweden, and in China as well, in our surface water and even drinking water. So that's why we use these chemicals in our experiments. And with 100 milligram per liters, and we put 4 kinds of membrane in. If just a PN nanofiber, polymer fibers, or even coated with aluminum hydroxide, you will see no impact on the concentration of these pharmaceuticals. However, when we convert it into LDH-like, doped with cobalt, nickel, or even with additional introduction of copper, and we can see the absorption capacity taking on with time around 15 minutes. And we believe creating the oxygen vacancy and introduce unsaturated metal side improves the absorption performance. And this just now previously was more about a batch experiments. And here we want to do is to introduce a flow through of the water. And what we do is that we have this nanofiber membrane and roughened by the LDH absorbents. And then we stack those membranes together to become a more filter column. We pass the water from one side and collect from the other side. The result we found actually, the removal efficiency is very much related to the retention time. So when we have a quite fast flow rate of the water, and the efficiency, removal efficiency is rather low. But if we can enhance or increase the retention time of the water inside of this filtration zone, then within about 440 minutes, they can last with the efficient removal efficiency about 85%. So of course, when it's beyond such a time and duration, then the saturation of the LDH happens. So the removal efficiency goes down. Then what do we do? Here, we found out our LDH has also the photocatalyst properties. And what we do is that we actually pick 3 different pharmaceuticals from the previous review articles, where they list the pharmaceutical they found in the surface water and also the drinking water. And we do the filtration once, and then we shine light on it to induce in situ degradation of the pharmaceuticals, and then we do it again, and we did for 5 times. And over the 5 times, we found that there is no decrease in the removal efficiency. So I believe this is a quite efficient way to induce the solar-driven regeneration of absorbents. And we also use USR to detect the radicals of hydroxide radicals in our catalyst and absorbent. In that case, we know that it is radicals to induce the degradation of the pharmaceuticals. So as a conclusion for the first project, we can say that from the our concept is first, we will start with a 3D constructions of nanofibers. It's a polymer substrate, so it's a flexibility on it, in it as well. And then we have the in situ growth of the functional materials with the capacity to absorb the pharmaceuticals. And in addition, we also have photocatalytic activity. So once they reach saturation, we can introduce a light source and induce degradation and regeneration of the materials. So the second project I want to introduce is another kind of functional material that is a piezo catalyst. So actually this project idea originated from one of the project with oil center at DTU. And for instance, if we go on the platform of the oil plate, and we will hear a lot of noise, feel the vibration, even the wind and the water flow in the sea. And this indicates the massive mechanical energy. So our idea is that instead of, for instance, the light source from the previous project, can we harvest mechanical energy around us or inside of the system and convert them into a chemical energy for the degradation of the pollutants in the water? And especially we are looking at nanofibers because such a one-dimensional structures that can amplify the mechanical deformation and thus to optimize the piezo effect. So what do we do is that often when we do the water treatment, there is aerations and technologies where we introduce air bubbles. And what we want to do is that if we have a wastewater, and then we have kind of a flexible and light nanofiber membrane that can flow on top. At the same time, we can supply the air bubbles, and these air bubbles will reach the top and have the explosion. And such mechanical energy released from this process can trigger this piezo catalyst materials and produce radicals for the degradation of contaminants. So this is the idea, and then we start our synthesis. Again, we start with our PAN nanofibers. So here you can see 3-dimensional microporous nanofiber membranes, and then we do the in situ growth of Indian cobalt morph. So you can see here is a kind of leaf structures and on the covered on the PN nanofiber surface. And after that, we do the sulfurization. So you will get an Indian doped copper sulfide. And the structure slightly change, but you can still see that each nanofibers are fully covered by this catalyst materials. So we put it into the water on top because it's super light and porous. It floats on the surface of water. Then you can see there is the tube introduce the gas bubble. And once there's a gas bubble come in And you can see those nanofiber black edgeless membranes will like dancing around with the bubbles on the surface of the water. And with 16 minutes, and you will see the color change lighter and lighter. And with UV detections, we can see the methylene blue, in this case, acting as organic dyes, and reduce as the concentration reduced significantly within 1 hour time. And also what we found is that this degradation efficiency actually is highly related to the air bubble rates. Here you can see the air bubble rates, and from 100 to all the way to 900 milliliter per minute, and you will get a different kind of degradation efficiency. From 100 to 700, you can see reached almost 95% degradation efficiency within 60 minutes. But the further increase will disturb the contact between the piezo nanofiber membranes and also contaminates. So too fast is also not efficient in this case. The other one we found out actually the flexibility play a role in this degradation process as well. To prove that, what we did is that we synthesized exactly the same piezo catalyst, the indium cobalt sulfide, on different substrates. For instance, this is a nickel foam and it's rigid. And compare with the nanofibers, it doesn't have any flexibility. We also use this catalyst as the powder and put it in the water as well. And with exactly the same procedures, and we found when we have the flexibility in our substrates, then the removal efficiency is much higher compared to the one that has rigid substrate, and also higher than the powder form. So in that case, the flexibility of the PN nanofiber did contribute to enhance the piezo effect. And the other one question often people ask is, can you recycle it? And what about the mechanical stabilities? So we did this for 5 cycles, and we couldn't see the deterioration of the performance. After these 5 cycles, we also take it to the SEM, and we see still there is no change in morphology, or there's no change in the nanofiber overall structure as well. So this, I think the mild air bubble process that induces the piezo catalyst activities, it's also quite how to say, it's not strong enough, like the sonication, what you find in the literature, and they can maintain the integrity of the nanofiber membranes. So here, as a short conclusion on the project 2, and you can see the idea is to use air bubble as a source of mechanical energy to trigger the degradation of contaminant in water with this piezo catalytic membrane reactors. And first, we actually invent a very novel piezo catalyst, this indium doped cobalt sulfide. And we can see they can generate the superoxide radical ions to induce the degradation. And the flexibilities of the nanofiber substrates also amplifies the mechanical deformation. And the air bubbles, not only they provide such explosion to transform the mechanical energy to the nanofiber membrane, but also this supplies oxygens. So to further enhance this generation of superoxide radical ions. And at the end, we also still have 3D nanofiber structure. So right now we have ongoing experiment trying to see whether we can have the flow through reactors, then further enhance the efficiency of such water treatment technology. So at the end, I also want to address some challenges I found in those projects, and want to propose some our way forward. One is about a gap between research and practical applications. For instance, I think there is still some collaboration between the researchers and also industry that can really contribute to this commercialization or realization of the work we done in the lab. For instance, the reactor design and how we can prevent the photocatalyst leaching if it's not immobilized. How can we ensure they can be reused? And also when we treat these micropollutants, the concentration is quite low. Is there any way we can use reactor design to improve mass transport? And how do we introduce the light source in the most efficient way? The other challenge is that when we do experiment in the lab, and often we simulate water in a very ideal way, but in the real world, we might encounter very complex water matrix. For instance, the natural organic matters or inorganic electrolyte that can act as radical scavengers, especially for the radicals. So in that case, maybe the lot of the experiment design in our lab might not work in the real complex water matrix. And pollutant concentration, especially for those pharmaceuticals or the CECs that are present at very low concentration, and how we can efficiently treat such pollutants and in this low concentration. The other one is toxicity. So when we do this catalyst design or the process design, we also need to look into the toxicity of both catalysts and the byproducts. So to make sure we are not introduce another toxic element into the treated water. And to promote commercialization, also need to combine our research work in the material and process with economic and environmental life cycle analysis. So those are the challenge I can see. And for us, there's not easy to close this gap. And what we do in our research group is that we try to reach out and collaborate with industrial partners and try to get their experience and their competence in constructing reactors, design the process, and with our invention in the lab. And also we want to make more design, the process design with material design and combine them together. And in our department, we also have a research group. They focus on environmental impacts for water, for chemicals, for the process. So when we design our water and when we design our materials and also membranes, we always had collaboration with researchers in that field as well to make sure we can have overall evaluation of what we do. So finally, as an acknowledgement, I want to thank my awesome research group members. And I think I moved into the new department and started this water technology activities for 2 years. But for 1.5 years, we had the Corona situation. And I have an awesome and very dedicated research group. They work even during this very tough time and create an amazing result. And I also want to thank the collaborators at DTU Environment, Professor Klaus Helix Nielsen, and Professor Henrik Andersen for their support, and also Professor Zalokai for the simulation work, my colleague at DTU Environment and also DTU Energy. At Denmark, I think we have quite nice funding instruments. For instance, the Innovation Fund Denmark, we got funding especially to promote the collaboration between research in the university and the Danish companies. So in that case, we can really reach out and try to implement the research outcome in the real world. I also want to thank the Center for Oil and Gas at DTU and Independent Research Fund Denmark and Novo Nordisk Fonden. Those are the instruments for us to try some crazy ideas and also carry out some fundamental research. So at the end, I also want to thank Member Society of Australia Asia, especially Professor Zhang, Professor Zhang, Professor Wang, and also Sue, and also Federico for inviting me, and thank all the participants today joining me as well in this webinar. So thank you very much.
Professor Wenjin Zhang. This is a very great presentation. Your presentation is very much colorful and beautiful and illustrative and very much informative. Thank you for the wonderful presentation. So now it's time for Q&A session. So looks like everybody want to talk to you. So if you have any questions, so please just unmute and then ask her directly. So anybody want to ask a question to her directly? Federico? Yeah, Xiwang, yes, please.
I want.
Yeah.
Oh, sorry. Angela, very, I think, interesting project you shared to us. Particularly the second project, you convert the mechanical energy and to trigger the catalytic oxidation. Could you explain a little bit more, how, we can convert the mechanical energy, how, use this process to drive the formation of the radicals? I'm pretty sure many of the audience might be wanting to explain a little bit more, but it looks like a magic.
Yes, thank you for your questions. I think it's a very good question. So this is a piezo catalyst for the water treatment. It's rather new. And so as a piezo catalyst, what they do is that if there is mechanical energy, especially they can trigger the deformation of the materials, then they will generate such voltage. And people want more, like in the literature, they try to generate energy, the electricity. But at the same time, if you put it into the water, get in contact with, for instance, the water molecular or the oxygen, they can also produce the radical, more process like a AOP process. And this one is particularly interesting for me is because we can combine the flexibilities of 2D, of 1D nanofiber membrane with the piezo. And in the literature, there has been some of the work done with like this piezo catalyst in water as a powder and with ultrasonication. So ultrasonication is a way to introduce mechanical energy. But for us is once we have ultrasonication, it's the mechanical integrity. If you try to immobilize on the substrate, the mechanical integrity is often it's questionable. And the other one is that we think ultrasonication is quite powerful, and that is a very intensive energy input. How efficient is overall processes? So that's why we were thinking, is there any efficient way to introduce this mechanical energy? That's why we come with flexible nanofibers with air bubbles. Because these air bubbles look as small, but once they get in contact with this nanofiber, they have a localized explosion. And this mechanical energy is actually quite strong, especially when your material is one-dimensional fibers and flexible. So in that way, we want to amplify, to try to minimize the energy input, but also increase or enhance the piezo catalytic effect.
Very interesting. Thank you,
Federico?
Angela.
Well, thanks again, Angela. It's fantastic to have you here. And as Sean said, I think it's really exciting work what you're doing over there. And also you have some really good equipment. So I'm sure this is just the beginning. Well, I'm definitely not an expert on this, but I think the first thought, still regarding to the piezo catalyst one, was whether it is worth trying, instead of just bubbling air, maybe bubbling oxygen or air with higher oxygen concentration or some other oxidants to kind of enhance this reaction that occurs between the
Actually we did. I think you are very right. The oxygen does contribute to the generation of super oxide radicals. And the reason we also even try to replace the air bubble with argon bubble. So in that case, we can see the decrease in the degradation efficiency. So we know the oxygen means additional source in this reaction. I think we haven't done that use pure oxygen. The reason is that we want to see whether we can apply it in the bigger scale. When you have bigger scale and you constant supply of oxygen, pure oxygen, there might be additional cost to the process. But during the, for instance, membrane MBR process or some of the water treatment, supply of air sometimes is a pre-treatment. So we see that there is advantage of just use air to reduce the cost of this mechanical energy input. But I think you are very right. If we supply the oxygen, that might have an additional boost to these piezo activities.
Okay, so next question is about Alan. Alan, can you please unmute and then ask directly to Angela?
Yes, hi. So I was thinking about the photocatalytic regeneration and whether you would do that with sunlight or whether you would utilize targeted wavelengths that will be more specifically active and therefore potentially more efficient that way. And would you do the regeneration while the material is also absorbing, so you're increasing its effective capacity, or do you need to take it offline in order to be able to regenerate it and then return it to service?
Yeah, that's a very good question. I think the introduction of the light source is always the part of reactor design. And for our experiment right now in the lab, what we did is we used a solar light simulator. So what we want to do is that this photocatalyst not only react or response to the UV light, but also just a solar light with a broad wavelength range. And the results you see it from my slides, that actually is only the introduction of solar light. And of course, how you can introduce such a light is another question. If we can have such membrane also filtrations and can introduce the lights. For instance, I saw some of them introduce light with LED lights and just to put it inside of the filtration unit. And that's a way to induce the photo degradation, photocatalyst degradation in situ. In that case, you don't need to take it offline or do it some other places. But the principle is that once you have the light source, you will be able to generate these radicals for the degradation.
Okay, Alan, is it clear for you? All right,
yes,
so
thank you.
I have one question, Angela. So I have experienced nanofiber. So when you say nanofiber, nanofiltration, NF, it's very confused. Nanofiltration or nanofiber. So
Yes.
make sure to mix it together. So as a membrane, people always confuse
Yes.
nanofiltration. NF is a more formalized form rather than nanofiber. Yeah, just I have experienced this area, and then the issue already addressed in your way forward in the last slide. You mentioned about the scale up. The nanofiber looks like you can manipulate your structure, you can immobilize, you can do a lot of things to do. However, so far as I know, there is no scale up commercialized nanofiber for water filtration, water membrane, water absorbent. So, in your view, how we can overcome this kind of intrinsic problem of the nanofiber, and then how we can make more scale up and commercialization? What's the best application we can target? What's your opinion?
Yeah, that's a very good question. And I have been asked this question many times as well. I think I have to stay optimistic, because I remember 10 years ago when I started doing electron spinning in the lab, it's only like one needle and very simple device in the fume hood. And it seems there's no hope for the mass production of nanofiber membranes. But now you can see there are many companies, they are trying to make the industrial scale electron spinning equipment. Marco are one of the most famous ones. And also when I travel to China, I also see some of the company has a very large scale electron spinning as well. I think the cost will decrease with the increase in scale. And what I can see is that if you have the simple electron spinning, for instance, you just have one polymer like PN nanofibers, and that can be produced at a relatively low cost. And for the additional design, if you start with this simple nanofiber membrane and make additional, for instance, we do the in situ growth and we do some conversion afterwards, and then that might minimize the cost from the electron spinning process. So for now, I remember that Marco had some of the cost estimation for such a membrane. For some of the polymer, like polystyrene or some cheaper polymers, they can receive a few euro cents per square meter. So quite promising. And the cost is going down with years as well. So I still have hope. Of course, we are trying to make this membrane in a more, niche application, where the consideration for the cost is less compared to massive wastewater treatment plants. That's one way to try to push the commercialization of the electron spinning technology as well.
All right, thank you for your nice answers. Any other questions? Last question from the audience. Otherwise, so please join me in thanking the Angela presentation. That's great to hear your great research area. Thank you, Angela.
Yeah, thank you for having me, and thank you everybody for joining this
All right. Can
webinar.
I make a screen share, please, Sue?
Yes, of course.
So just the last announcement. Can you see my slide? Yep. Okay. So next, our scientific and industry webinar series will be announced our date through the email, and then Professor Xing Yang, she's from the Belgium KU Leuven Institute for Sustainable Metals and Mineral. So she will talk about her research area. So please join our next webinar. Also, let me announce our IMSTEC conference. Wenjin Zhang and Michael Duke. So they will organize the IMSTEC conference November next year. So Angela, you are very welcome to visit to Australia. So you can have another year progress of your nanofiber research in Melbourne. Also drop by Sydney, and we can very welcome your visit to Australia. And also, I'd like to thank
Thank you.
everybody during this pandemic and difficult times. Everybody participate and then join this webinar. I wish you all the best for everybody and then stay safe. And this time will go very soon. Thank you very much, and then see you next webinar together with Professor Xing Yang. Thank you to Professor Wanting Wang, Professor Xiwang Zhang, who are the co-organizer. Also Su Long, she is the coordinator of this webinar series. Thank you, everybody. Thank you.
Thank you, Sean. Thank you, Angela.
Yeah, thank you for
Thank
having
you,
me.
Angela.
Bye.
Stay safe. Bye.